Well, the standard model is based on a symmetry called local gauge symmetry. And in local gauge symmetries, the masses are zero, but we know the masses in nature are not zero. So there has to be a mechanism to break this symmetry. The mechanism that is put into the standard model is a so-called Higgs mechanism. And the idea there is that all of the space is filled with a field called the Higgs field, and that when particles interact with the Higgs field, they acquire mass. And that is the point of view. And the Higgs field is an important pillar of the standard model because it gives these particles masses, and of course particles in nature have masses. So it is important that the Higgs be discovered to confirm the standard model, as the standard model is written down today. However, if the Higgs is not discovered, there probably is another mechanism. In fact, there has to be another mechanism, which will be equally interesting, that is required to break the symmetry, to allow the standard model to be an operative model. And there are some candidates for it, for such a symmetry breaking mechanism. And there are probably types of effects that we don't even know about which would do the same thing. So if the Higgs is discovered, it will be a great triumph for the standard model as it is written down. If the Higgs is not discovered, I think it is practically certain that there is something else in nature which is equally interesting and maybe even more interesting that will create the symmetry breaking required by the standard model. And why do I say it's required? Because the standard model is so good. It accounts for everything we observe at current accelerator energies, and even the initial results of the LHC give great confirmation of the standard model. So if the standard model is so good, symmetry breaking must be there. There must be a mechanism. If it's not Higgs, it is something else. The atom is a very complex thing. It has electrons going around a central nucleus, which is made up of neutrons and protons. And the neutrons and protons are made of other particles which we call quarks. And that is what we're able to observe. And the way we observed them was to use the equivalent of a very, very high-powered electron microscope. It was, of course, the linear accelerator at SLAC. And we were able to peer inside the proton and see little point-like objects inside, which were identified as quarks. Well, quarks are fundamental building blocks of nature. Quarks, all atoms are composed of quarks, only quarks and electrons, and that makes up all atomic matter. Now, the atomic matter is made up of two kinds of quarks, called up quarks and down quarks. However, there are four other types of quarks: strange quarks, charm quarks, bottom quarks, and top quarks. And there are a number of very interesting questions associated with this family of quarks. First of all, why do we have 6 quarks? These quarks also have incredibly different masses. The lowest mass quarks are the up and down quarks, and they have masses of a few million electron volts. The top quark, which is the heaviest quark, has a mass which is heavier than 185 protons. It has a mass of 173 GeV. GeV is 1,000 MeV. So you can see that these top quarks are incredibly heavy. The question is, why are they so heavy? And what role do they play in nature? The other question about quarks is, are quarks the most basic building blocks of nature? Do quarks contain other particles? Now, there are some very interesting aspects of quarks being made up of other particles. Quarks are incredibly small. They're smaller than about 10 to the minus 17 centimeters. To give you an example of that, if I take a carbon atom and expand it to the size of the Earth, how big would a quark be in comparison? Well, it would be smaller than a half a centimeter. And so it gives you an idea of how tiny quarks are. And of course, that's the upper limit in the size. They could be much, much smaller. And the LHC will be able to actually increase the effective magnification of observing quarks and be able to see whether the quark is smaller than 10 to the minus 18 centimeters. In other words, they can demonstrate whether quarks are smaller than 10 times smaller than the upper limit that we now have. Now, if quarks were made up of some other particles, there would be another very interesting feature, and that there would be some new forces in nature which would be at least 100 million times stronger than the so-called strong force. Now, to give you an idea of how strong the strong force is, if I hold two quarks side by side, they're attracted by the equivalent of about 15 tons of weight. Now, imagine a force 100 million times stronger than that. And that's just the lower limit in the size. The force could be a good deal greater if the quarks are actually smaller than 10 to the minus 17 centimeters. So there are some extremely fascinating issues associated with whether quarks are fundamental or not. And also the idea that we have this family of enormously varying masses is another perplexing question, which I would hope that the LHC might give us some evidence toward understanding this particular question. Because of the incredible energy of the LHC, it will increase the magnification by a factor of 10, and this gives us the opportunity to observe the smallest things in nature with greater precision.
That's great. Perfect.
Well, there is a question as to whether there is a fourth generation of particles. It would be extraordinarily interesting if such a generation of particles existed. At the present time, there is no compelling reason in the theory to suggest it, but science is always looking for the unexpected, because absolutely any theory that will go beyond our theory, our current theory, will give us unexpected features. The Standard Model has three force fields. The strong force, which holds the nucleus together and holds quarks together to form the proton and neutron. The weak force, which is associated with particle decays. And the electromagnetic force, which of course we all know about in everyday life, but it's the force which holds the atom together. It holds the electrons in the atom. These forces have fields, and these fields have particles associated. There is a wave-particle duality in quantum mechanics. So every field has an associated particle, and we call these, for these fields, vector bosons. So the photon is the quantum of the electromagnetic field. The Z and the W are the quanta of the weak field. And we have the gluon, which is the quantum of the strong field. W prime and Z prime would be quanta of new fields. And this would indicate that there were new fields in nature which we are not aware of. But if these were discovered, it would be exceedingly interesting. And so looking for a fourth generation, looking for additional gauge bosons like the W prime, the Z prime, would be extremely interesting because it would point to a theory that goes beyond our current theory and would give us a better view of what the universe consists of.